Okay, it looks like we got the majority of everyone, so I think we can get started. Hello, everyone. I am Paul Jones, and I'll be taking you through this webinar on extension performance. Um, Before we get into it, I do want to make just a couple housekeeping notes. Um, for starters, this is a Zoom webinar. For those of you who haven't been to a Zoom webinar before, you might have noticed the controls look a little bit differently. There's no option to unmute yourself. The way it works in a Zoom webinar is if you have a question or a comment or something you'd like to bring up, you can click the raise hand button in the tools, and that'll let me know that you have something that you'd like to say or ask. And then whenever I notice it, whenever I get to a good point to pause, I will give you the ability to unmute yourself, and then you can ask your question. Additionally, there is also a Q&A section where you can ask questions. That will work just as well, whichever you prefer. What else? Right, so this webinar. This webinar is some of the output of a very long research period. I've been, well, I and others have been working on this for, I don't know, 3-4 months. We've been doing research into performance-related issues within CET, ways we can improve it, looking at the tools we have and how we can improve them. And we've even have a team that's been dedicated towards hunting down performance issues in manufacturer extensions and working with their development teams to get them improved. So we've put a lot of effort recently into improving the performance of CET and its extensions. And this webinar is very much the output of that. The presentation itself that we're going to go to is going to feel a bit thrown together in certain places because it kind of is. While we were doing a ton of research into this and gathering up a lot of sources for it, we in the end realized it was probably more important that we get this information out as soon as possible. And so the actual presentation was put together quite quickly. However, that leads into what I think is some good news. This webinar is only the start of this. We're going to keep developing this. We're going to keep adding content, refining the content that we have, and eventually it's going to be turned into our first self-paced training module that we'll be making available to everyone, most likely for free. So all the same content you're going to see plus some more is going to be refined a bit further and be made into a set of independent videos that you can click through, view the sections that you want to. They'll be more focused, so if you want to spend more time learning independent each section, then you can, or not. That's the benefit of making it self-paced, is that you can focus on the parts that are important to you. Right, so this webinar is broken into two halves. The first half that we're going to start with is going over some of the tools that we have available for getting performance data out of CET and its extensions. And then the second half will be on more high-level concepts. We're going to take a real hard look at caching and how that can be done and improved, and then just some general, I guess you can think of it as tips and tricks regarding performance in a way. Because this webinar is so long, we will take a quick 5-minute break when we're transitioning between the two halves, just so everyone gets a chance to stretch their legs or get a glass of water or whatever. But housekeeping aside, let's get into it, start talking about stuff. So we're going to start with tools. Specifically, we're going to start looking at P-time. A lot of you have probably seen P-time before, and you can think of it as a special syntax that wraps around microtime. P-time is the most rudimentary of the time testing tools that we have. I like to think of it as like the PLN at performance tests because it's so easy to use. You just add in the keyword P-time, you give it a string, just something that you're going to recognize later, and then you encapsulate the code you want to test inside of curly braces. Then when the code block completes, you're going to get an output that includes the string you gave it, as well as how long it took to complete that block. So the output, pretty simple. Using it is pretty simple. You just wrap some code you want to test into p-time, and you'll get some output telling you how long it took. Um, p-time also works fairly well when it's being nested. So if I bring up a more complex code sample here, this is some code that allocates supports along a run of something or other. It'll gather up all the conflicts. It'll gather up each support's like supported placement options, and then go through and find valid placements for everything. So if we add in this global p-time, well, not global, like this big picture p-time, it's going to trace the entire function, and then start placing more p-time blocks inside of it around important chunks of the code, we can get not only how long each of these different things take, but also get a bit of context. If I were to run this code, I'd get this output here. I can see that the whole thing took about 2.5 seconds. That's what that last output is there. And that the initial like step, the gathering all the conflicts, only took 23 milliseconds. So I can tell in context, this is almost nothing. It took very little time. So p-time is it's a very, oops, sorry, I clicked around. There we go. Sorry about that. It's a very quick and dirty way of doing some time trials. Like I said, it's kind of like PLN. In fact, really, p-time is really just a wrap around some calls to microtime and some PLN statements. So it's good for quick tests, but it's not super accurate. You may have noticed that some of these outputs here, the place support from positions, most of them take 100 milliseconds, but every once in a while it takes over 300 milliseconds. So even though this wasn't super accurate, we did get some interesting information. We'd see that sometimes it takes unusually long to place these supports, and so we know there's something there we might want to look into and debug further. Um, had a question come in. Can you call out the package the syntax for p-time is in? I should know that off the top of my head, I don't. I want to say it's in CM Basic if I had to guess, but when we get to break, I'll look it up to double check. Right. So p-time, it's quick, but oftentimes if we're doing some more serious performance tracing, we're going to want some more information. We're going to want some more context. So for that, we have two tools available. We have probes, which we'll look at a little bit later, and we also have the profiler. The profiler is a pretty handy tool. Basically, when the profiler is active, when it's like recording or whatever, it will track calls to every method or function that get called. Based on this, it'll provide a lot more information about their runtimes and their how many times they're called and things like that. Um, it provides a ton of information, which means the majority of the effort you're going to put into using the profiler is actually just to refine that information, slim it down to just the information you want and making sure it's sorted in the way you want. This here is a real quick example of how the profiler looks. I don't want to focus on the syntax too much just yet, because so much of the profiler is about controlling the output. I want to look at the output first, so then we can start talking about how we can work that information down. If I were to run this code here, which is just some code that runs through all the snappers in the drawing and grabs their bound, the profiler would output all of this. So there's, like I said, a lot of information here. And we'll go through it all. Sorry, I lost my place in my notes here. There we go. So we'll start off with the actual function. On the right hand is the actual function or method that was called, and all the other data for that row is relevant to that to that function or method. Next to that is the package that defines that function or package or method. We have these two columns for per call time. The profiler does track the fact that these functions are possibly called multiple times, and these per call columns show you how long on average those functions took to execute each time. Whereas next to them is how long in total those functions were running or executing. The first two columns are under inclusive time. So this means these are tracking how long these functions were executing from start to finish. So if you were to put in a micro time at the beginning of the function, then another one right at the return statement, this is what you'd get. So the wall clock time, you might think. Opposed to that, there is also these columns for exclusive time. These list out exclusively how much time was spent in these functions. If ever the control flow went out to another function, that is not recorded. So this is specifically time in this code. Then next to that, you have this exclusive percentage. So this is of all the total time spent in this function, how much of it was specifically in this function, exclusively in this function. So you can think of this kind of as exclusive time divided by inclusive time. And then finally, we have a column that indicates how many times this function was called while the profiler was running. So what does using the profiler look like? First, you need to configure your filters. There are different ways to filter down that data. Actually, I want to call out something here. You may have noticed that these functions are from all over the place. There's some from core, there's some from Fika, there's one from my profile, one from Active Office. It's from all over the place. And chances are, if you're debugging your extension, you probably don't care about everything under the sun. You probably only care about the parts that are within your extension. And so that's one example of what I mean by filtering. You can restrict what gets put into this report down to perhaps just your extension or maybe everything except your extension, things like that. So that's why the first step of working with Profiler is to set up your filters. There are different ways to do that, and we're going to look at that in more detail here soon. But I just want to get through the quick version of what the profiler is like. You then start the profiler to start it recording and start it listening, more or less, and then you stop it when you're done. Whenever you want, you can generate a report. This is another method on the profiler object. It just generates a string that is that report. So more than likely, you just want to print it out right away. And then when you're done with all of your testing, you call finish on the profiler. This is really important to do because this is what cleans up all of the data that's recorded so far. If you don't clean it up when you're done, then the next time the profiler gets run, you're going to get some really confusing results. I have this listed out as these 5 steps. However, there isn't any reason why you can't actually start and stop the profiler multiple times. So if you want to have more fine-grained control over when what gets recorded, you can just repeatedly start and stop it. There's also because profiler is a global, or actually it's a function that retrieves a global, you can do all of these things from different places within the code. For example, you can start it in one place and stop it somewhere else. This can come in handy sometimes if you're just trying to figure out what all happens during some event. One of the things I had actually used a profiler for a while back. I wanted to know what all goes into actually inserting a snapper into space. And so I had started the profiler inside of the button, the actual library button that starts the animation. And then I stopped it when the snapper entered the space. And so the profiler caught all of the functions and methods that were called in that time. And so I got to see everything that happened, which is a really good way to diagnose performance issue there. I wanted that to be really smooth. I didn't want the user to feel any lag when inserting a snapper, so the profiler helped me out. Um, there may be a time when you want to regenerate the results more than once. That's perfectly fine as well. The profiler will remember all of its data as it keeps going. It's not until you call finish that it actually throws out any of the data that is collected. Right. So this profiler is available from runtime debug. So you'll want to use that one. And then the first thing you'll need to do is set up your filters. There are three ways to set up your filters. You can do a whitelist method where you specifically call out the packages that you want to profile. And you do that by using the include method on the profiler. This one takes a package and it will tell the profiler to start recording for that package. This does not include sub-packages, so you'll need to include all those as well. At the end of this webinar, I'll show you how to, or tell you how to get to the code samples that come with this webinar, and then include a little helper function that will, for a given extension, dump out all of the packages that are inside of it. So you can use that as a way to profile your entire extension if that's what you're looking to do. An alternative to a whitelist approach is to just profile everything. In the code sample you saw before, that's what was happening. This does what it sounds like. It doesn't have any restrictions on what gets profiled, just it's everything. Or you could work in a blacklist style where it will profile everything except what you tell it not to. This is done with the all to say start profiling everything and then make specific exclusions using the exclude method on profiler. For the sake of keeping the code on screen a little bit concise, I'm going to stick with just all for now, but any of those different approaches will work just fine. You start your profiler with the start method, and then you have your code that you want to have profiled, and then you stop it. In this case, it's just a single line of code, but there's no reason why it can't be a lot of code or even stretched out over many files. Once you've got your data that you want, um, you generate a report. And this is another thing that needs to be customized in order to get the data you want. The first argument to report is how many lines you want it to output. It'll include the top X number of functions sorted based on whatever sorting scheme you give it. The sorting scheme is decided by the second argument. It's a symbol, and it tells it what to sort on. By default, it will use this £i, which means sort all of the results based on total inclusive time. So the functions that take the longest total time to run, start to finish, will be towards the top of the list. You can also sort based on the average inclusive time per call, or you can switch to exclusive and exclusive time per call, or you can just sort on the total number of times a function was called. So again, this indicates what kind of sorting scheme it will use, and then you'll also provide that number to say how many off the top should be displayed. And then finally, tell the profiler that you're done with it by calling finish. This will actually throw out all of the data it's collected so far. A question came in, can the include exclude methods take in wildcards? I don't believe so. I won't promise you that, but I'm pretty sure that it doesn't. Another question came in, can we dump the report in a text file directly? Should be able to. It's just a string, so you should be able to write it out to file. There's no helper built into Profiler to do that for you, but we do have I do think we have like an easy mode, write the string to file function available, probably in CMIO. Another question, can you talk again on the difference between exclusive and inclusive? Sure. So let me step back a couple. Come on. Oh, there we go. So there's basically three ways that you can filter out what functions and methods actually show up in this report that gets generated. You can use the include method to tell it specifically what packages to consider, what packages to record. You can say all, which means just record everything. Or you can use all in combination with exclude to tell it specifically what packages not to record. So by doing it this way, it will record anything except what you tell it not to. Which one you choose is entirely up to you and what you're doing. In some cases, one approach might be better than the other. I myself have never used this blacklist approach. It's kind of weird to say I want to record everything except this. I have always used either the all, just profile everything, or I've used the inclusive to just have it record function calls within my extension. Sorry, I meant exclusive, inclusive in regards to its being in the final profile report. Oh, I see what you mean. Sorry. Let's see here. Well, I'm going to do this the hard way. Oops. So we want this one here. So inclusive time means the time from that the function started to the time that the function stopped, that entire time. So you can think of it as just running a p time around the entire function, basically. Whereas exclusive time is basically that same time, except for time spent in other functions. So this is like inclusive time minus the time spent in other functions. So it's if you were to actually like pull the code up on page, specifically the code that you're like seeing on screen. Both of them have their value. Exclusive time is good for tracking when you're trying to figure out where you might have expensive code, where you might be doing too much work. But sometimes the error isn't that you're doing too much work. Sometimes the error is you're calling other functions that are doing too much work. And so inclusive time becomes useful. Right. There we go. Is it possible to set a common unit for measuring time? So I'm assuming you mean like output everything in milliseconds or everything in seconds or something. I don't believe so, but that would probably be a good feature request. I know they're actually working on what they're calling a profiler 2.0, which is going to be a newer profiler that outputs easier parsable data. I think they've talked about adding a GUI front end on it, things like that. So I would say if you have any feedback on the profiler, now is a great time to send it into dev support, and they'll send it along to the team that's working on that. Wouldn't that mean that inclusive time should be lower than exclusive? Sorry, I said the backwards. Exclusive would be less than inclusive. Yes, exclusive is always less than inclusive time. Well, I suppose in an absolute, if your code doesn't call anything else, then exclusive time would be equal to inclusive. But yeah, in every other case, exclusive would be less than inclusive time. Right. So what's it like to actually use use this profiler? We have a lot of practice with this one. This is a tool we've had around for quite a while, but it got some refinements recently as part of our like internal performance hunting teams. And it got used a lot by these teams to hunt down issues. However, What everyone who's used it has found is that while the profiler is good in catching everything, it tends to produce too much information to be the only tool you use. Um, the pattern that a lot of developers use this is they'll start with a profiler. They'll take some entry point that they know goes into the code that has a problem. They'll throw the profiler at it, and they'll use that as a kind of a smoke test to figure out roughly where problem is. And then after that, they'll start using more um, targeted tools. Um, for example, probes, which we'll talk about here in a bit. So yeah, you'll start off with a profiler, and then once you have an idea of where to look next, you'll start using tools that are more targeted, less shotgun. Um, Getting a handle on how to like sort and filter data does take a bit of time. It's not terrible. I got the handle of it, within I don't know 20, 30 minutes, but it is something that you do need to look to look at and get good with. So, what a lot of developers did was they would start with Profiler and they would follow it up with either like very manual things like p time and PLNs and the traditional approach, or the use of probes. Probes provide data that is very similar to Profiler data. However, it's way more targeted or designed to be more targeted. Um, Whereas the profiler is just recording all function and method calls, the probes only record what you tell them to record. So in some ways, they're kind of like p-time in that you place them down, you tell them where to start and stop. But they have a lot of advantages over p-time. The biggest one being that they will collect more data, but they can also aggregate data. Um, So probes can be hit multiple times, and then we'll record how many times they've been hit. They'll record things like average time per call. Um, I'm not sure if it's been merged in yet. We also added an exclusive time per call in there as well, and things like that. And we'll look at some of the output here in a couple of slides. So how do they work? You start by initializing a probe, by calling init probe and giving it a key. Then, like the profiler, you need to start and stop the probe to tell it to like what it should record. When you're ready to output your data, you can just call probe report. This will just print out the data to the console. And then when you're done with the probe, you destroy it. Note that it is completely safe to call start and stop on a probe that hasn't been initialized. It just won't do anything. And in fact, that's kind of a handy trick I've seen used in a couple places. I've seen developer leave calls to start and stop probe lying in their code, sometimes commented out, sometimes not, um, and they just won't do anything until they add some code in their extension to actually initialize a probe. Then suddenly they start getting outputs. Um, I have to remember, if I remember correctly, it is the probes that are written in such a way that they get compiled away in release mode. So I have seen some developers who will leave them in their code. I don't know if I'd recommend that. You're gonna have to make that choice for yourself, but it is an option because it shouldn't affect runtime performance at all. There's one additional step. You're never going to be working with a single, well, you're going to rarely be working with a single probe. The profiler is just one thing, so when you destroy it, it's dead, but probes, you have a whole bunch of them. And so the actual data that gets collected isn't stored on the probe itself. It's actually being stored on a kind of probe manager. And so when you're finally done doing your diagnostic session, you want to call reset probes. This will reset all of the data that's been collected and clear it all out. You want to be sure to call this every time, or else the next time you start using probes, you're going to get some confusing data. Sorry, I lost my place here. There we go. So the question came in, so probes won't work in release mode. That's correct. They actually have like a preprocessor directive that makes it so they don't even compile in release mode. They just get compiled away to nothing. Right. So like p-time, probes get better when you use them as nested. And so here we go. What we have here is a short little function that is aligning some things. It will gather up a bunch of things. It'll check for some special case, and then we'll call it align them. I don't know specifically what this does. It's not really important. But we want to run some probes on this to see how long everything is taken, how many calls there are to align, and how many special cases we hit, things like that. So we're going to add a probe first around the whole thing. This will measure the total time taken by this algorithm here. Then we add another probe around that first part that's checking for special cases. And then we add another probe around this align so that we can see all of the alignments actually happening. And if we were to run this, we would see an output kind of like this. So it will record the total time taken by that probe across all of its calls. You'll see if it was called many times, what was the minimum time and maximum time, median time, and then average per call. You'll also notice in the report that on the left-hand side, two of them are indented from the other one. This is because those two inner probes, special case check and align thing probes, those were started and stopped while the align all probe was still recording. And so the system considered them to be nested underneath them, and so it will automatically indent them. This is really good as you start focusing in your probes. You run this diagnostic, then you start looking inside of one of these probes and insert more inside of it, get more and more refined probes. They'll all appear nested in here to indicate like which one is inside of which. Question came in, is there some syntax for stop probe and start probe? Yes, there is, and we'll look at that in a couple slides. So, you may have noticed while I was putting this code sample together that there is a lot of boilerplate that needs to be added. Every probe needs to be initialized, then started, then stopped, then destroyed. And on top of that, you also need to generate reports and do this reset. So there's a lot of, well, every probe that you add is going to add at least 4 lines of code, which can get kind of tedious. There are a couple things we can do to make this easier in these cases. For one, we can use, instead of initializing and destroying each individual probe, we can use these all functions, init all probes and destroy all probes. What this does is it sets a kind of a global flag that just says, consider any get probe to be initialized. So when you call start probe, it doesn't really ask the question if this specific probe is initialized. It just says, yes, that flag is set, assume it is initialized. And destroy all probes just unsets that flag. This is perfectly fine. This will save you a bit of typing. Just keep in mind that if you do have any probes that you've left lying around, just uninitialized, that they will be initialized now. So you might see their data show up in your reports. Additionally, as was just asked, there is a syntax to make the start probe and stop probe easier. And it's basically the same thing as p-time, except it's just the word probe. So you use the word probe, you give it the key or the identifier for your probe, and then you wrap the code you want to test inside of curly braces. So if we do that for these other sections, it'll end up looking like this. This has the added benefit of being more visually clear about what you're recording, what's being probed. Question came in. Does the profiler do similar indenting for function calls within another function? No. My guess would be because because the profiler is recording everything that happens, it's not necessary. Well, also, and because it's summarizing multiple calls to the same function, it would be really hard to respect that tree. For example, if one function was called from two other functions, what does that look like? So no, the profiler does not do the indenting thing. So how we've seen the code for probes. What is using them actually like? The best strategy that I've seen for using probes is to first place them around the entire system or function or whatever it is that you want to test. And then inside, you start placing probes around every major logical section of the code. Um, just as an example, let's say you've got like an A-star algorithm running inside of your extension and you wanted to test how well it runs. You'd have one probe around the entire algorithm, then you'd have one probe around requesting the next node, another probe around evaluating its neighbors, another one to collect new neighbors. There's off the top of my head, there's basically 3 or 4 major sections of the codes. You'd have 3 or 4 probes in there to measure each part of it. The output would tell you where all the time is spent and how often those things get hit. And then you'll use that to figure out, well, if the probes show up that this chunk of the code is really expensive, well, then you can start focusing in on that. You can start looking at the functions that are called or the code that's being called and add more probes inside to get more specific data. And you just keep iterating on that, getting more and more specific until you find the code that's not performing well. Next up, we have a working example of how you might use probes closer to real life. But it needs a little bit of setup. So for this hypothetical extension that we're going to be diagnosing, the developers are looking to diagnose a problem with their part system. When they originally made their parts generation system, they knew it was going to be expensive. Their parts need to have a discount schedule applied to them. So that discount schedule needs to be read from disk. If that discount schedule isn't there, it needs to be pulled in from the web. And then that discount schedule needs to be applied to every part via their SKU code. Now, when they wrote this, they knew it was going to be very expensive. Web calls are, or disk calls are very expensive. Web calls are crazy expensive. And then because it applies to every single part, it scales pretty hard with the size of the drawing. So they knew this was going to be bad, and so they implemented a caching system. They implemented the system so that once a particular SKU that came up, it would generate the part for it, doing the expensive work, but then saving it so the next time they wouldn't need to do this again. And they initially saw some really great results. The caching helped quite a bit. But recently, their caching system has started to not help as much. Their parts generation has gotten really slow recently. And so what we're going to see is an example of how you would trace down that problem using probes. This next section is the actual using this is pre-recorded. So I'm going to click the next button and it'll start playing a video. Let me double check that I'm sharing audio. I believe I am. Yes, I am. So you should be able to hear a narrator as it goes on, but if not, let me know.
We'll start by placing a probe in rebuild native part list in space. This function is found in CM core in a file named
Oops.
native partlist.cm. This function is the best place to get the big picture of parts generation. It includes the calls to fetch the parts, as well as merge them and process various hooks. By starting here, we can capture the majority of the process and lower the risk of missing something. Since this is our entry point for testing, this is also where we will initialize our probes, destroy our probes, and generate the report. Next, we'll add nested probes around each major section of the code. This doesn't give us very refined results, but it gives us clues about where to focus next. Running the test a couple times reveals that the initial assumption was correct. The parts are taking a long time to generate. Even though we didn't learn anything new, this was still an important step to take. Part hooks such as the post-finalize after merge hooks are notorious for being performance pits. We'll leave these probes here, as they will still serve to provide context to the next probes. Moving into the fetch parts function, we can see that there isn't a lot going on. There is some caching, but that would have been cleared out by other code. There is also a chunk of code that deals with filtering parts. Neither of these segments of code are likely to be part of the problem, but adding probes is quick, and it's always important to prove your assumptions. As we expected, the time is spent in the internal fetch parts function call, so we'll continue focusing in there. At first glance, this function appears to have a lot going on. However, most of these are just adjustments to flags, early bailout conditions, and managing the progress bar dialog. However, there are a few interesting sections of this code: run pre-fetch parts hooks, internal fetch parts, run raw part list hooks, update part tag, and finalize flattenable keys. There is this large chunk of code here. However, this is behind the merge flag, which is set to false when this function is called. As before, we'll add probes and rerun the test. The report shows that the majority of the time is spent in internal fetch parts, so we'll continue focusing there. Most of the code here is just iterating through the snappers in space and calling fetch parts on each one. Since there is only one part of this code that does any real work, we can skip adding probes here and simply jump into the fetch parts call. Now we've worked our way down to the snapper level. This is where we will see one of probe's strengths in action. The probes will record each event they are triggered for and aggregate that data. If we place a probe here, we'll be able to see how often this method is called, how long it takes on average, and how long all of the calls take in total. In a normal situation, you might choose to jump straight to the getParts method and continue from there. This method is marked final, so there are no overrides to consider. Also, it's unusual for extensions to override the before getParts and after getParts methods, so it's unlikely that a problem could have been introduced here. However, for this exercise, we'll practice diligence and continue using probes all the way down. As usual, we'll place probes around each portion of this code that appears to perform work. Note that there is a recursive call to fetch parts here. When placing the probes, we have to be careful not to include this code because that would cause our probes to stop recording at the wrong time. The results tell us that the work is in the getParts method call, as expected. We'll add probes to the getParts method on our snappers next. This code has 3 steps. Check the cache for an existing part, generate a new part, and add it to the cache. The test results are not too surprising. Almost all of the time is spent in the section that checks the cache. If we assume that our cache is operating correctly, that would mean that our cache is returning values more often than it isn't. If we look at the number of calls, it would seem that the assumption is correct. The next step would be to go into the part cache key method and add probes there. However, this is an abstract method and will be implemented differently for each snapper. To figure out what snappers to look at, we'll use a trick with the probe keys. We'll add the class name to the probe key here. This will result in a separate probe getting created for every subclass. The probe report gives a clear indication of who the culprit is. This particular snapper is taking up almost all of the time, and the average time per call is enormous compared to the other snappers. Let's continue the search there. And here is the problem. A naive programmer thought that the most accurate way to retrieve a cache key was to generate a part and extract the key from it. Unfortunately, this completely negates the benefit of having a cache at all. The solution here is to generate that key by itself. This was a very short and contrived example, but it does demonstrate the process of using probes. Start big and work your way down through increasing levels of specificity. While doing so, it's a good idea to leave probes in place until you are finished. They can provide context and avoid occasional false positives. Also, consider that while problems like this one may seem obvious when looking at the whole picture, it is common for developers given a task to not have the full picture. As a result, these kinds of errors can be introduced by anyone.
Right. So we are at the end of the section on tools. Are there any questions about anything we've seen so far? Okay. I had promised that once we got to the halfway mark, we would take a quick break so everyone can like refresh their glass or take a stretch if they need to. So we'll do that now. We'll take a 5-minute break. I think that takes us to 9:56 when we come back, and then we'll start up on the next section. Okay, and welcome back. So I had a couple questions come in over the break. Let me look at them real quick. Um, if I understand right, we are not supposed to use any performance tracker inside a recursive function. Am I right? The probes will definitely get squirrely if you use them inside of a recursive function, just because they go entirely off of key. And if you're starting and stopping with the same key, then it's going to stop at strange times. You could probably work your way around that somehow, but it would take a little bit of effort. Um, the profiler, I don't think cares about recursive functions. At least I don't think so. There was a question about where can the recording and the examples be found later. Once we have this webinar recorded and published to YouTube, I'm going to update the briefcase post to include a link to it. But otherwise, it'll just be available on Configura's YouTube channel. So you can find it there. The code samples will be in the dev training repo. I'll talk about that again at the end of the webinar, but that's where they're going to be probably today. Probably right after this webinar, I'll submit them. And yeah, that's where you'll be able to find everything. So let's keep moving. Probably the biggest chunk of this second half of the webinar is going to be on caching, just because it is such an important topic. And I done lost my notes. Here we go. So caching is a really popular technique to use as a technique for improving your extension's performance, mostly because it's really easy to implement usually, and it is unique in that it can improve the performance of your code that is theoretically already optimized to its extreme anyway. So if you take some code that generates a value or produces some kind of output that can't be made any better, caching might be able to actually improve the performance even further. Um, I'm going to whip through a quick explanation of how caching works, just for those who might not have set up a caching system before, or maybe have just followed examples but have never had anyone explain it to you. So the way a caching system works is it's all about generating a value once and then reusing it as many times as possible. Sometimes you'll cache single values, and sometimes you'll cache large quantities of related or similar values together. If you are saving a lot of values, if you're saving more than one, you're likely going to store them in a map that'll have some kind of a key that we call a cache key. Technically, any kind of value can be a key for a cache, though usually it's a string. Not always, but usually. And that's just because strings are an easy way to serialize complex data, so they do fairly well as caching keys. But it all depends on what your cache is doing and what kind of values you are caching. You might use a Boolean as a cache. That would be a little strange, I suppose. You'd only be caching two values, but you could. Maybe you're caching on integer if you're caching in, like, say, by an index or something. There's lots of ways you can do it. If you're caching a single value, it might look something like this. Any of you who've worked with libraries, for example, you've almost certainly seen code that looks like this. The way it works is you'll have some global value that will be your cache. It'll start off uninitialized. Then you'll have some kind of an accessor function or method that retrieves the value. If the value hasn't been initialized yet, it will be initialized, and then finally it's returned. The benefit to doing this is that you only pay the cost of constructing the value the first time. As soon as this gets called again, you're potentially saving time for the user, because you don't need to regenerate the value again. You can just keep using it. It gets a little bit more complicated when you're talking about caching multiple values. So right here we have an example of some code that adjusts parts based on a discount schedule. Those discount schedules are, for whatever reason, difficult to construct or difficult to load or whatnot. So we want to have a caching system for them. And so what we have here is a system that will generate a caching key. In this case, we're using a string. It's gathering up some data, in this case, gathering up some data from part tags. It's asking the product for what product line it's from, and it's using that data to construct a caching key that is then used to retrieve a data, some values from the cache. If the value isn't in the cache, it's constructed and added to the cache so that it can be reused later. This style of caching is only really a benefit if that same key, that same situation comes up again. Um, if every time this code is called, you're generating a new cache key, resulting in a new value being generated, then really the cache isn't doing any work for you. But if it's more likely that this cache will be hit with the same value a bunch of times, then you save a lot of time. And then this form is another way to do caching of multiple values. The difference with this approach is that all of the caching has been extracted out to a separate function. So now the calling code can just call that accessor function, just say, give me a value. Here's the data that tells you what data I want. And all of the cache management is encapsulated inside the function. This is nice when you can do it because it makes the code, well, it makes it more readable. That just parts method isn't cluttered up with a bunch of caching information now. It's just closer to the relevant parts of code. And similar for the caching function, it's dedicated to just managing the cache. So this is nice whenever you can pull it off, but you can't always pull it off. This is only doable in situations where that caching code also knows how to generate the values that will be cached, which isn't always the case. As an example, if you're caching, well, if we talk about DSP data has a caching system built right into it, and it can do that because DSP data already knows how to generate its parts, and it knows how to cache them, or how to generate a key for each one. And so it can contain all of that caching stuff right inside of the part. You don't need to add anything to make that happen. You just need to enable it. Whereas if you talk about, say, graphics on snappers, if you have, 10 different snappers, they're going to generate graphics in 10 different ways. And so a shared graphics cache can't know how any individual snapper should generate graphics. So it can't be asked to generate values for the snappers. If that's up to the snappers to manage the cache in those situations. So the majority of the rest of this section is just talking about some high-level concepts, some tips and tricks, and ways to make sure your cache is used to the best effect. First, I want to talk about this concept of cache last. There is, with most developers, either a conscious or a subconscious assumption that caching will just fix poorly running code. If you have a chunk of code that is inefficient, just throw a cache at it and then it's problem solved. This really isn't true. Keep in mind that caching is not about eliminating this code that's being cached. It's reducing the number of calls to it. Caches will reduce how often you need to generate these values or generate this output, but it doesn't eliminate them. If the code you're trying to cache is still poorly performing, it will still be poorly performing after the cache is added. Just to make that point a little bit stronger, consider an extension that has a really inefficient parts generation code. It takes a full second to generate every part. Now consider a drawing that has 10,000 products in it in 20 different configurations. Without a cache, this drawing will take the better part of 3 hours just to generate all the parts in it. If we add a cache, That brings it way down to just 20 seconds, more or less. Now, it's really easy to look at this and think, well, sweet, we made a win. We improved this by several orders of magnitude. There's nothing left to do. The problem with that kind of thinking is you're really ignoring the fact that your parts are still taking a full 20 seconds to generate. That's still a really long time. Considering how often parts are generated, how many places where parts affect the user's experience, 20 seconds is still just way too long. The underlying problem hasn't been solved. The problem is still that parts take a full second to generate. That's way too long. And so I guess the point I'm trying to drive home here is that caches are not going to make your values construct any faster. It's still on you to make sure you're optimizing your code as far as possible. Caches just give you something to add on top of that. And so that's why I describe it to others as cache last. Improve your code as best as you possibly can, make it run as fast as you know how to, and then consider a cache. There are actually some situations where a cache isn't necessarily useful. I had hinted at this before, but in a situation where your caching code is generating a lot of unique values and those unique values aren't ever asked for again, well, then your cache isn't really doing anything for you. Cache is only useful when the system asks for a value that it already has. That's the only time you save any, CPU or memory. So it's important before you add your cache to your code to consider whether or not it's a good idea, whether or not you're actually going to benefit from it. It's really easy when we're talking about a single value. So going back to this single value cache, or like I said with the library, it's really easy to look at this code and work out whether or not you're actually going to make any uh, um, advances using this. As soon as this function is called the second time, you're saving time. The second time this function is called, you have avoided the object's construction and you made up that time. Also, the cost of developing this cache, the cost of managing this cache in runtime is almost nothing. So the benefits easily dwarf the costs. However, that gets more complicated as your code gets more complicated. As you start caching more values, it gets to be a little bit more uncertain whether or not you're actually going to be getting more cache hits or misses. This code on screen has a ton of variation in its part number, which is going to be used as a cache. It varies a lot based on dimensions. There are a lot of different electrical configurations, and each unique combination of all these values results in different part, which represents a cache miss at least once. If the system is repeatedly asking for the same parts again and again, yeah, the cache is a help. But if instead it's just asking for unique values every time, then you're paying the cost of generating these cache keys. You're paying the cost of these cache lookups, but you're still generating values every time. So you're not really getting any benefit. In fact, it's actually worse to have a cache in that situation. So how do you know? How do you know whether or not your cache is going to be somehow helpful? There is a quick trick you can do, and I'm going to walk you through here. Just a couple lines of code you can add to your file just to get a feel for whether or not a cache will be any help. So we're going to look at this code here. This is code that generates graphics for this snapper here. What it does specifically is not important. It's generating a value, and we want to see if adding a cache will give some benefit. So what we're going to do, we're going to add a global set of keys, and we're going to add a call count. Inside of our code, we're going to generate a hypothetical cache key. We'll try and get it accurate to what the caching key actually would be. And then we'll add the caching key to that global set, and we'll increase this call count. So just these quick 5 lines of code, and we are not actually adding a cache. We're just getting some metrics on how often the cache will hit or miss. If we run this on a good sized drawing, preferably a user drawing, then we get some metrics as to, excuse me, how many hits and misses we get. I ran the test in one situation and I got 4 unique keys after being called 100 times. So this tells me that the cache is probably going to help a whole lot. This means I only had to generate 4 unique values to go into the cache, and then I basically got to reuse values 96 times. So there's a lot of time saved. If I got a different result, if there were a lot of keys compared to how many times the thing was being called, well, then maybe this cache isn't actually that helpful. Again, caching does come with some cost to it, both development time, maintenance time, and runtime. And so in this situation where it's generating unique values so much, it might actually be a detriment to add a cache. I might be adding more work than I get any benefit from. Um, I won't walk through this on screen, but you can do more or less the same test using probes. Um, it'll look similar. You'll still add a cache key to your code. You'll add that cache key set to your file. But then what you'll do is you'll just add 2 probes. You'll add a probe that measures the whole value, the whole thing you're trying to measure, and then you'll add a probe that only gets triggered when a unique key is hit. This will tell you how often you get hits and misses. It'll also tell you how much time is spent generating values. And so it'll also tell you how long theoretically you would be spending if you had a cache. So you get some more hard data on whether or not a cache will be helpful. So this is a really handy way to do it. A question came in. Will we talk about the possible drawback of increased memory consumption with large caches? I will be talking about the effects of memory on performance eventually, but in regards to caches, yes, it's kind of the same situation. If well, let's jump back a couple steps here. If PowerPoint will let me, we'll see here. I want to go back to, come on, big guy, this one. There are tons of ways that you can get different caching keys from this code. So your cache will likely have a lot of values in it, which is going to result in really, really large caches. Large caches means your lookup times will increase slightly because they're hash maps. Typically, you don't need to worry about that too much, but just having a larger memory footprint is bad for a lot of reasons. Users have limited RAM to spare. Plus, like I was hinting at, like we're going to talk about in a little bit, memory just has an implicit performance cost to it. Just having a thing in memory will cost you performance. But like I said, we'll get there later. So yes, so this is, I didn't get to it in this webinar, but another thing to consider when implementing a caching system is maybe also implementing a mechanism for resetting your cache and clearing it out at some interval. Maybe you do it on a timed basis, like over a certain amount of time. Maybe you reset it when it gets to a certain size. Maybe you reset it when the user opens a new drawing. But if you're going to have a cache with a lot of values in it, you should consider clearing it out on some kind of regular interval. I've seen another question came in. I've seen the keywords keep and static being used when caching single variables. Are there any differences between them? So I think, let's go back to this one. This code could have been written a little bit differently. Do I don't think I have an example of it. This code is using some kind of a global variable to cache a result. I could have instead declared this variable inside of the function and just mark it as being static. When a variable inside of a function or method is marked static, it means that the value is kept between calls to that function or method. So in effect, it's kind of the same thing as declaring a global. I don't know of any performance difference between the two approaches. So at least for now, I'm going to tentatively say use whichever approach makes the most sense to you. I personally tend to use a static variable inside of that getter. I think it makes it a little bit more concise. and keeps things more local. But I know there are others that don't like the static keyword just because it's not commonly used and makes it less readable. The keep keyword. Now this one, I admit I need to know more about, but as I understand it, the keep keyword is strictly a develop mode flag. As I understand it, keep just says between, I want to say between sessions of CET, like when you stop CET and start it up again, it will attempt to keep that value. But like I said, don't quote me on that. I would have to look it up to be more certain. Note was added, keep shouldn't have any effect in runtime. Yeah, exactly. It's specifically a develop mode thing. Right. Oh, and I lost my place. Let me see if I can find it. Next, we're at that. We did that, and then we're on to, right. Cache keys have a huge impact on how effective they are and how much time they actually save you. A good key will make it so you're getting cache hits more often, saving you more time. A bad key will get you cache misses far more often, which can even cost you time if it's done poorly. Um, in addition to that, assuming we're talking about strings, the longer a string gets, the more time it takes to actually perform the lookup. Even with a hash map, you're going to have to perform some string comparisons at some point. And the longer your key is, the longer it takes to look it up, the more time you spend just managing your cache. So simplifying your key down as much as possible is a really important thing to do. A common mindset that a lot of developers have when making their cache keys is to include every input that is used by the value being constructed. Right. So if you have some, if you're caching some 3D and it uses width and depth, then your cache key should include width and depth. This kind of mindset will work the majority of the time, but it won't work all of the time. A more effective strategy for your cache keys is the mindset of provide a key that uniquely identifies your value. Sorry, I'm catching up on my notes here. You want to uniquely identify your value. I'm going to say this a couple times because it's a really important thing and it can make a really huge difference. A key should uniquely identify your value. It's not really about catching or encapsulating all of the inputs. It's related, it's close, but it's not quite the same thing. So let's actually look at an example to make my point here. So what we have here is some code that's caching a part. It's generating the same part every time, or the same like skew every time, but the part quantity changes based on the width. If it's over a certain width, you get 6 of this part. If it's under that, you get 4 of this part. And then what I'll also do is I'll keep on screen here some metrics of how long, how many times we get a cache hit and how often we get a cache miss. So right now, this part that's being generated, I've artificially inflated how long it takes to generate it. I think I set it at like 10 milliseconds or something. I don't know. I don't remember. But I made it take a little while just to make these numbers a little bit more obvious. You can see right now it's taking over 2 seconds to generate all the parts for this particular drawing. So let's look at the caching code a little bit. You can see we are generating a cache key here. The cache key is made up of a skew number, a width, and a depth. But what's interesting here is that most of those things aren't even used. The skew code is constant anyway, so that's kind of wasted time. Width is used, but depth isn't used at all. So now we're including depth as part of the key for no reason. this means that there are more ways the cache key can change, more ways that it can vary, which means more value is being generated, even when you don't need to. The only important factor here is width. So why are we using any more than that in the caching key? So if I change this key to just include width, and I run the same test again, you can see that my results have improved by an order of magnitude. The results are way, way better. There are less ways that this code can change. There's less ways that we can get cache misses, so we save a lot of time. So this is following the mindset of just include all the inputs that are relevant, that are used by your code, by your caching code. However, it can actually be taken even further. If we look at this code, it's only doing two different things. It's generating a part if it's greater than a certain length, and it's generating another part if it's less than a certain length. So really, it's not even about the width. It's about whether or not the width is over a certain limit or not. So if we update our cache key to instead just do the same thing, is the width over that certain limit or not? Now we get even less variance in our caching keys, and we get way, way more cache hits, saving us even more time. And you can see in the results our time spent in parts improved by another order of magnitude. Things are way, way faster still. This is the point I really want to drive home, is that keeping your keys as simple as possible while still uniquely identifying your values will have a huge impact on how efficient your caches are and how much time you're saving for the user. So yeah, keep your keys as simple as possible, but also as short as possible. Something I'd hinted at is that as your keys get longer and more complex, then we have to put more effort into looking things up. So in addition to simplifying them, also, I say minimize here, but what I should have said was shorten them as much as possible. Use as few characters as possible, because it actually has a pretty big impact as well. Simplifying them, as we just described, is a big help, but we can do even better, actually, in order to get a good cache. So we don't actually need the cache key to contain the data that we're caching with. So if from the previous example, width was the important value, technically we don't actually need to use the width as the caching key. We just need to generate a key that uniquely identifies the value. So if we can accomplish that in a reproducible way, we've won. So what are some ways we can do this? What are some ways we can still uniquely identify our data, but without inserting any more information to our cache keys than we need to? Let's take Booleans, for example. Booleans, if all you do is append them to, say, a stir buff or something, or append them to a stir, then it's going to perform a 2s on that Boolean, which will generate the string true or generate the string false. So 4 or 5 characters, 8 or 10 bytes. Which means that for a single Boolean, which can only exist in 2 states, we're sucking up as many as 10 bytes of memory just to represent that. Which means your cache keys are going to be a lot longer than they actually need to be. If you instead convert it to a single character, now you can get the exact same effect. You're still uniquely identifying each of these conditions, but now you can do it with a single character. Distances or doubles, depending on how you store these values. These are another big one. In fact, it's actually a bigger deal here in North America than other regions because we're still stuck with the imperial system. But all distances in CET are stored as meters, which means whenever we define something in inches or feet or even centimeters or millimeters, it has to be converted to meters first. And in that conversion, we're probably going to add a lot of numbers after the decimal place. Now, in memory, it's all the same size. A double is a double is a double. But when you convert that to a string, that actually is a bigger deal. because if there are a lot of values after the decimal place, that means you're putting out a much larger string. So the way to solve this problem is to convert it back first. We actually have a number of helper functions that do this for you. For example, inches s. This is a function that will take a double, will divide it by inches, and then output a string. If you do it without changing this show unit argument, it'll actually output a little quote mark as well, like the inch unit. So I just turn that off because really we only need the number. So if we originally stored a value of 12 inches into a variable, if we were to just print that out as a 2s, we're gonna get this nice big long number that has like a million numbers past the decimal place, because that's just how you convert to meters. By calling inches s, we'll convert it back to inches first, and then it'll just output 12, just 2 characters, which is much shorter and still conveys the important data. It's unusual for angles to be part of a caching key, but there's no reason they can't be. We can do something similar here. Angles are always stored internally in radians, which almost always have a ton of decimal places to them. In degrees, the string would actually be much shorter, and that's why there is this helper function 2ss available. This will take the angle, convert it to degrees, and then output that as a string. There are probably some others that I didn't think of when putting this slide together. If so, I would love to hear about it, either in chat or comments, whatever. But the principle is the same. Try and keep your caching strings as short as possible while still being accurate and uniquely identifying your value. Let's see here. There are also some things to avoid when building up your caching keys. One, never use this. This is a transient value, meaning that it is something that can be changed over time. For those of you who don't know, this is basically a pointer to yourself. However, objects get moved around in memory all the time. The undo system will commonly swap things around. The garbage collector might shift things around in memory to optimize the space it's using. So this is a very inconsistent thing. It's always a reference back to yourself, yes, but it's always a reference to a place in memory, which will change over time. So it makes for really bad caching keys. For a lot of objects, 2s is a bad thing for the same reason. I think the default 2s method just looks at your class name and then an ID, which is made out of your pointer. So it's not very consistent, and so it doesn't make a good caching key. I say on the slide here, avoid using class.name. I really should have said be careful with it. If you're making your cache at a lower level and it's something that's going to be used by multiple subclasses, then every subclass is actually going to have a different name, resulting in a different caching key, and it may or may not be what you want. If it is what you want, if you want every class to have its own entry into this cache, then yeah, this will work just fine. But more than likely, if you're implementing it at a lower level, you meant for it to be shared. This might seem like a silly thing, but it's something we've actually seen a couple times in our performance hunting. Don't use the value that you're going to cache to generate the key to cache the value. At a passing glance, it might make sense. Surely the value has all the data it needs to generate the key, but if you're generating the value, well, then you've completely negated the benefit of the cache anyway. So never do this. Also, don't use any random or arbitrary values. So don't use randi or GUID to generate a caching key, simply because if a value truly is random, then there's no way to get that value back again. You can't reproduce that same caching key, which means you're just going to get a cache miss every time. I see a comment in chat. where we crammed up to 8 bool values into a single byte. Oh, nice. So this was a comment from Nathan saying that basically they did some bit cramming of multiple booleans down into a single byte to make their keys even smaller. That's pretty extra. If you can pull it off, if you have 8 byte or 8 different booleans you need to cram into a caching key, then hell yeah. We've even got some helper functions. I don't know where, but we have some helper functions available that will do things like bit masking and stuff to pull that off. Question came in, is it planned to make it possible to use tuples as keys? I'm not aware of that. Yeah, I haven't heard any efforts to make that happen. It's going to have the same problem as using a lot of reference types as keys. It becomes a question of what is it that actually is the key? Is it the reference to that thing? Is it the pointer to that thing? Because that's going to have the same problem as using this as a key. It's a value that keeps moving, so it gets really hard. And so you need a unified way to hash these values consistently so they generate the same key. And with tuples, that's going to mean hard coding some rule around it. So I haven't heard anything. That's not to say that it won't happen. I haven't heard of it. All right. So this is the end of my section on caching. Caching is a really powerful tool, but it can be used in a really poor way, resulting in really poor performance, or used correctly, it can improve performance by huge amounts. It's you just have to do it carefully. And also maintain it carefully. Keep in mind that when a cache was set up initially, you might have made some assumptions that turn out to not be true later, which degrades the performance of the cache. So always be on the lookout for ways you can validate that your cache is still working as intended. Finding the proper test case for checking the caching mechanism is a major challenge, definitely. And we're actually going to be talking a little bit about that, or kind of adjacent to that here in a bit. User drawings are always the best bet. They're not perfect, but since we're always targeting improving your user experience, having a user drawing gets us as close as possible to that, especially really big user drawings. Those are really the best. So if ever you can get your hands on a big user drawing, definitely do that and run their tests there. But yeah, it is definitely a trick knowing whether or not this was a good test. Did this actually prove anything about the cache's effectiveness? It's tricky. Just takes experience. Well, probably more luck than experience if I'm being real. Okay, so this next section is just some quick rapid fire general tips on how to write really good performant code. And some of these actually apply even more to just performance, just general good developing practices. So always test with realistic drawings. This sounds familiar. Because we're trying to simulate the user experience, because we're trying to optimize the user experience, using their drawings is always going to be the best option. This is where we're going to get the most accurate test data, or at least the most accurate that we can imagine. So as much as possible, you get user drawings. This isn't always going to work though. Sometimes users have security restrictions that they need to consider. Not all of us are in very tight communication with our users. So the alternative is to make synthetic testing drawings. This is tricky. It's really easy to make a fake user drawing that is basically just set up the way you want to make your code look good without even realizing it. Or maybe it doesn't reproduce some situation that you didn't think of. So it takes some practice, but I've got some general tips here. Whenever you're making your own artificial drawing, make sure it has at least 10,000 snappers in it. That's a good size drawing, and that's not uncommon. This will really put the performance of the drawing to test. If you have products that come in different configurations, try to place all different configurations in the drawing. If you have snappers that might react differently to being connected to things, then try connecting those snappers in the drawing, or having some that are connected, some that are not. And if you're unsure, then pretend like it might be, because sometimes it'll surprise you when connecting things has an effect. Be sure to include unrelated snappers to what you're testing. So maybe this means adding snappers from other product lines, or even better, try adding snappers from other extensions. Fika Office is a really good way to do this. When you're making your synthetic drawings, make a couple 4-packs or something with Fika products and include that in your drawing. There's always the potential for interaction between extensions that is worth considering. And then don't do this by hand. Inserting 10,000 snappers into a drawing will take too damn long. And if you're good about it, you're probably going to be doing this fairly often for different situations. So do this all with code. What we have here on this slide is a little, it's a very small example, but it is an example. This is actually the code I used to generate a test drawing for that probes example, the pre-recorded one. All of that test drawing was done using this code. You can see here it iterates 10,000 times, creating a semi-random snapper every time and then placing it somewhere. Now, if I was making a more realistic drawing, I should be doing things like also attempting to snap them together. I might also include some snappers from other extensions, stuff like that. But do it all in code, because then you can easily reproduce it. Later on, when you're in a different situation, you can just tweak your code to generate a new drawing, stuff like that. Question was asked, any suggestions on how to generate a drawing with all possible permutations of a given snapper? I wish I still had, or maybe it might actually be in the code samples, an example of that where I had a snapper with an entire width domain, a depth domain, and what I did, it was run a couple of for loops that were iterating through every element within those domains and generating a snapper for each one, or at least I think I actually did like 10 snappers for each one. Things like that work. If you have prop defs set up, that's actually a pretty convenient way to do this. You can iterate through all of the prop defs and all of the values within their domains and set them that way and generate a unique configuration for each. So yeah, there's different ways to do it. Another big one. This is a thing I feel like I say it to every developer who asks me to help them debug their code or help them find a problem. Almost every time I'll end up saying, don't assume anything. Almost every time this happens, a developer who's been banging their head into the wall for 2-3 hours trying to find a piece of code that's not running correctly or is not performing well, at some point they'll stop and they'll say, oh, this can't be the problem because this always generates this value, or this is always true, or this never happens. And every single time I'll stop them, I'll say, prove it. And it'll turn up wrong. And then they found out that they just wasted 3 hours of their time tracing down something completely unrelated. Don't assume anything when you're doing just debugging in general, but even with doing performance testing. Don't assume that this value will always be this or whatever. It's an easy way to lose time. Remember that a code that you assume to always do a thing is code that you're not looking at. It's code that you're not measuring. It's code that you're not diagnosing. So be really mindful of times when you make those kind of assumptions, and then just take a quick second to prove it. It takes no time to drop in a quick PLN and just print out some value that proves your assumption. And if it turns out you were right, well, whatever, it only cost you a PLN, it's nothing. But a lot of times it will catch something that you would have otherwise missed and save you a lot of time. As much as possible, share memory and avoid the construction of objects. as I was getting to earlier, memory has an implicit cost tied to it, a performance cost. Anytime you just having a value that exists, that is memory that needs to be allocated, needs to be deallocated. If it's a reference type, then it needs to have reference counting. Eventually, the garbage collector will need to come in and deal with it. If it's an object, it's going to need to be constructed. There's a lot of work from just a thing existing. As a little example, this is one that surprised me. I had this little line of code I was using. I think I was testing out the profiler or something. Um, and this line of code really surprised me. It looks pretty innocuous. It's just doing a bunch of string concatenations. It can't be that bad. But what I had learned from running this code is that it actually generates 20,000 string buffers and 20,000 strings. Those are 40,000 allocations that need to happen, 40,000 constructors that need to be called, 40,000 references that need to be tracked, and later 40,000 objects that need to be destroyed and cleaned up. There is a ton of work happening just because of these two, what looks like just two little strings. Now, that was a sort of an extreme case. It was a magnified case. In the majority of the time it takes to do these things, to allocate an object and to even reference count it and destroy it is really, really small, usually. But once things get to a really high order of magnitude, once you're talking about 10, 100, a million instances of this thing, then suddenly these allocations and these reference counting, these things that are very quick become really, really expensive, just in the whole. So don't worry about this in the small sense. Worry about this more in the case where you have code that's going to be run a lot or very often. So parts code, graphics code, things like this. Avoid constructing any values or objects that you don't actually need to. As much as possible, try sharing the same values. Things like, well, sometimes with string buffer, it's faster just to clear it out and use it again, for example. Actually, a funny one. I don't have this in the slide, unfortunately, but there is a common problem with string buffers that most people don't know about. A lot of people, when they're using a string buffer and they're done, they want the output. They'll just call 2s, saying, "Give me the string. I want it now." 2s actually performs a copy because the 2s function or method actually assumes you're going to continue using the string buffer, and so it has to copy that string out so that you don't mess with the original. There is actually an alternative to this on string buffer called retire 2s. It does the same thing. It'll output a string, but instead of doing a copy, it just gives you the string that it's been building up the whole time. So it's a lot cheaper. It avoids a copy. So whenever possible, use string buffers retire 2s instead of just 2s. But it's the same problem. It's more construction of objects for no reason. So as much as possible, try to reuse values. Caching is a great way to do that. Caching is all about reusing values, but even on the small scope, there are ways to do it. And this next one might seem a little silly or maybe obvious, but just do less. Consider the cost of everything you do. Whenever you're looking at a code trying to improve it, just look at it and say, is there anything in here I don't actually need to do that doesn't need to be done? And take out all the fluff. Also consider maybe you have some code that's running and it's doing some work to generate a value or an output or a function or whatever that provides a pretty minimal benefit to the user. Maybe just improves their life just a little bit. That might sound like a nice thing to do. As developers, we tend to think that we've got CPU to spare and we've got memory to spare because we're working on usually a fairly powerful machine. And we're only running with like 1 or 2 extensions at a time, so we've got plenty of headroom. And so we say, yeah, this chunk of code here that provides this benefit is pretty fast. It doesn't feel that bad at all, so why not? Keep in mind though, users are not in the same situation you are. Users are always running with multiple extensions. For commercial interiors, for example, it's pretty darn normal for them to run with 30 extensions or more. It's very normal. In other industries, there's still going to be competition. There's still going to be a ton of other extensions running. So you're in competition all the time. You're sharing CPU with a lot more extensions than your own. You're sharing memory with a lot more extensions than your own. And on top of that, users' computers typically suck. They're usually not as powerful as yours, maybe not as much RAM as yours. So they have tighter constraints than you do. So when you do that work to add that minimal benefit, you might say, it's a little, it's a little bit of work, but it's not that bad. And when it actually gets to the user machine, it's probably going to be really bad because their situation always is more intense than yours is going to be. Well, apparently, not in the case of Tyler. Apparently, he's working on a potato, according to the chat. But yeah, really consider all of the code that you write because everything comes at a cost, and it's going to cost the user more than it costs you. Yeah, whatever. Oh, right, this one. This one always bothers me. Having sat down several times to help developers do performance improvements on their extension, it's very common for it's very common for a developer to get to some point of the code and be like, oh yeah, don't worry about that. That's always slow. That should never be allowed. Never let yourself do that. Never let yourself dismiss a piece of code as always being slow. It is theoretically possible that that code has been optimized to the point of just being pristine, cannot possibly be improved any further, but it's not very likely. More than likely, there are improvements that can be made. And if it can't, then there's other options as well. Caching as an option, or maybe spreading that work out a little bit using something like a task or an external process is an option. There's always ways you can improve slow performing code, and you should never, ever accept a code as being unsalvageable. There's always a way to improve it. So just when you're developing, be mindful of the code that you're just dismissing out of hand as always being slow. And then make a specific plan to come back and deal with that later. Make a specific, maybe it's just a date in your calendar, you say, go back and fix this code. Or maybe you put it in your Scrum backlog to tackle in an upcoming sprint or something, whatever it takes, but make a plan to deal with it. Don't just let it sit there because that's something that's affecting the users all the time. The users can't dismiss it. Okay. I have one last section, and I'm going to try and rip through it pretty quick because I see we're running out of time. We only have about 10, 11 minutes left, and I want some time for questions. So, like I said, this webinar is largely the product of a lot of experience we've gained over the years, but also we've had some dedicated performance teams here at Configure recently diagnosing internal and external extensions. And so we've learned a lot of lessons. And there are certain parts of the code extensions we found to be, this is like commonly where performance issues come up. And so I just wanted to touch on some of those places and talk about them a little bit. Parts is a big one. It's why so many of the examples and exercises that I've done have involved parts. It's because parts is one of the big ones. Parts is very a common piece of code. Parts run a lot. They run very, very often. They are relevant to a lot of different systems. And just the running of them is very complicated. All of the individual snappers in the drawing are going to generate one or more parts based on whatever configuration then that they're in. But sometimes you also have higher order considerations as well. So for example, maybe you have products that are ordered as part of a kit or part of a package. Then you need to do some after the fact logic to combine and deal with parts even after the snappers are generated. Sometimes you have to incorporate things like discount schedules or lead times into your parts. There's a lot of stuff that goes into parts. There's a lot of work to be done, and there's a lot of parts to generate in. It's a rough one. It's a really easy one to go bad. So how can you tell? As as I've said a couple times now, test on good drawings, test on large drawings, if possible, test on user drawings. Make some kind of a detail change in the drawing, maybe change a material or stretch a thing and see how that feels. It should be nice and snappy. You shouldn't notice any visible hiccup or lag after you make that change. If you do, I mean, it could be a lot of things, but one of the things that could be affected is parts. Because like I said, parts come up so often. If you want a slightly more targeted test, try doing a hard invalidation of parts. In dev mode and possibly in release mode, I can't remember. If you open up the calculation dialog, hold down the shift key and hit refresh, this will force a rebuild of the parts. It'll invalidate any parts that the space might have cached and goes to all the snappers and says rebuild them all, run all the hooks, the whole 9 yards. So this is a really good hard test of generating parts. For a really big drawing, say 10,000 plus snappers, this should take 1 to 3 seconds. And even that 3 seconds is a pretty long time. If it takes longer than that, you know you've got work to do. If you want some hard data, if you actually want to insert, say, some probes or the profiler or something, this function rebuild native part list in space is a good place to do it. This is in CM core in a file called native part list. This is a nice high level place where this function will call fetch parts and all the snappers. It'll also run all of the hooks like merge hooks and after merge hooks and stuff like that. So yeah, a good place to insert some testing code. Ways you can improve your parts, same as generally everything. Caches are a great way to improve parts just because they happen so often without needing to be reconfigured. So caches usually get a lot of hits. So a lot of time to be saved there. Do less, like I was saying before. I've seen a lot of parts code that does a lot of unnecessary calculations just in case. And just waste a lot of time that didn't need to. So just be very careful about how much work you're putting into caching or into generating your parts. Graphics are another big one. Graphics are, I mean, obviously they're used quite a bit. I mean, the users are working in a 2D or a 3D or both environment. The biggest problem with graphics, though, is that graphics are typically made very, very complex. And while complexity itself isn't a problem, it hides inefficiencies. It's very easy when looking at code that does graphics and just look at them like a method at a time and to not get the big picture and not see that you're actually doing things holistically in a bad way and doing a lot of redundant things. And we'll look at an example of that in a second. To actually get a good metric, if you want to measure how well your graphics perform, it's actually a little bit difficult. There isn't a really good place in the code to just drop in like a profiler or some probes. So we have this code on screen. Don't worry too much about copying this code. It will be included in the code samples. But this is a helper function that we whipped up that you can drop in your profile or in your extension, wherever you want, and it will regenerate all of the 2D and or 3D graphics in the space by default main space, but you can provide any space you want. By default, this code is set up to use the profiler. You can swap this out for probes. You can change what packages the profiler looks at, do whatever you want with it. But this is just a good starting place to get some testing code for your graphics. And like I said, this will be in the code samples. Question came in, what is pprof end? Oh, I should probably take that out. There is a couple of helper syntaxes for the profiler, and pprof end is one of them that will, I think that will generate the report as well as reset the profiler. I didn't use them in a lot of cases just because I found them the syntax to be a little limiting. I had a lot easier time just calling the methods manually, but in this case, pprof end is just a shorthand for generate the report and shut down the profiler. So how can you improve your graphics code? As always, consider caching. And a big one is make sure your caches are using accurate caching keys. This is a big one we found to be a problem in a lot of extensions. The caching keys were just really inefficient, generating too many cache misses or just taking way too long to generate their caching keys, things like this. That cache key has to be as fast as possible and as accurate as possible in order for the cache to be of benefit. So really focus on that. There is also a lot of objects being constructed unnecessarily during the construction of graphics. It was very strange. I don't know exactly where it comes from, but there's a lot of cases where objects were just being constructed to pull out a value and then use that to build your graphics. Strange stuff. And just be aware that if your code is sufficiently complex, it's probably hiding some inefficiencies. And I want to look at an example of that. So this pattern that you're seeing on screen is fairly common. I have it here for 3D, but the same thing applies to 2D. You'll have your entry point into your snapper, which is get 3D in this case, and then that actually forks out different parts of the code to generate different parts of your graphic. The get3D method will generate a sequence of primitives and then combine them into an instance. The other like supporting functions will do the same thing. They'll generate a sequence of primitives and then combine them into an instance. If you were to look at any individual function, it doesn't look that bad. However, when you look at it as a whole, you see that we're constructing a lot of sequences and we're constructing a lot of instances for no real reason. At the end, these graphics are all going to the same place. So why not just take that sequence from before, pass it into our supporting functions, and let them just append their primitives to the list. This saves from constructing all the sequences. It saves from constructing all those instances, which saves a lot of time, a lot of object construction, and even saves you some code. Additionally, and this is more specific to graphics in this case, in 3D, well, both 2D and 3D. Rendering an instance 3D that has a really deep tree of instances within sets, within instances, yada yada, is more complicated. It's harder to render things that has that deep of a tree. Keeping things nice and flat, like we see here, actually makes it render better as well. So yeah, just be aware that complexity can really easily hide inefficiencies. And then I'm down to the last minute, so I'm going to fly through this last one. Bounds. This one is probably not a surprise to anyone. Bounds are super important, not because they're especially difficult, but when they go wrong, they go really wrong. When bounds perform badly, it's felt intensely by the user because they're used in so many places and so often. Bounds affect how the snapper is put in the BSP. It affects how the snapper is found again later in space. It affects snapping behavior. It affects so many things, and it's used so often. When it's bad, it feels really bad. You can inject some tracing code inside of system local bound, but a much easier way is just to use the snapper performance tracker. This will get you the same data, and it's a lot easier. This is available from the debugged menu. You just select your snapper, bring up this dialog, or in either order, and then you'll get some times here. You can see in this case, my bounds took way too long to generate. You should be targeting about a microsecond for your bounds, which is actually really easy to do. If you just build a box based on your dimensions, that'll do it. Be careful with inheriting or sharing the local bound method from other places. For example, work surface has its own local bound method built into it. However, it implements it by looking at the work surface path, and then from all of the lines and arcs and all that stuff, construct a box that encapsulates all that, which is really expensive. If you were to write it yourself, you could definitely do a much faster job of it. Similar thing with DSP data. It has a local bound method, but it largely calculates that from all of the models. It'll look at all the meshes and try to construct a box that includes all of those triangles, which is, of course, really expensive. So just do it yourself. It's much faster. And spacebound caching. This is a feature that's built into all snappers. At least I believe it's available for all snappers. You can turn it on by simply returning true from use space cached bound. And then anytime you can invalidate your current bound, the one that's currently cached, just by calling invalidate cache bound, passing in yourself. This works really well, and it's really easy to implement. So you can actually get caching on your bounds for nearly free. Okay, so the code samples. All of the code samples that you've seen on screen, as well as a couple that I didn't put on screen, are going to be available in the developer training repo. They're not in there this second. I'm probably just going to go add them right after this webinar, but you can find all of the code samples in the dev training repo under the performance package. Yeah, and that is it. We made it. I thank you everyone for your time. I know this ran a little bit long. I apologize for that, but I hope this was helpful. I'm going to say goodbye to everyone who has to take off, but for anyone who has any questions or thoughts and wants to stick around, please do. I'll stay here and I'll address any questions. But yeah, for the rest of you. Yeah, there. Suddenly my headset spontaneously decided to just turn itself off, so I'm back now. Had a question come in. I assume that it makes sense to run the performance test in only release mode, avoiding the dev specific code. Both are good. Being able to test in release mode is definitely useful because that's going to be closer to the user experience, sure. But in dev mode, we also have a lot more diagnostic information available. The runtime tracks more information to give you either more data or more accurate data. So really both is good. I wouldn't exclude one or the other. Question came in. What is the performance routine that you use? Same set of codes. I keep only the testing application open to measure the more reasonable time. Have you faced any similar situation where you are inconsistent results in measuring time? So the question is basically about getting accurate or repeatable performance information. Sometimes that is a bit of a trick. So the performance routine that I go through would be I start with a kind of like we do with probes. Well, I have a one big picture function or method, one big injection point, and then I'll throw the profiler at it or probes at it, and I'll start from there and work my way down, running the test a couple times at each level. Now, this is where you can get into the situation you're describing where you run the test once and you see it takes 3 seconds. You run it again, it takes 30 seconds. What the heck happened? Why is it so inconsistent? That is a bit of a trick. The only thing I can suggest is include that as part of your testing. So for example, if you're using probes, you add your probes around the different sections of your code, watch for one to spike. And then if once you find the one that spiked, start narrowing in on that and just keep running your test to trigger that spike again and again. That's the best case I can think of. Unfortunately, spikes do just happen. If you're testing on a really, really small scale, if you're down to like the millisecond or microsecond level of timing, you're going to risk getting hit by the garbage collector or something. And so you're going to get some sudden spikes that way. Or maybe that's when the garbage collector isn't doing a collection, but maybe just shifting some objects around. So that can cause time. Maybe a task suddenly kicked in to do some work. On the very small scale, there are some small spikes that just kind of deal with, and that's why you always run your performance tests. I usually say like 5 times each, just to keep on lookout for spikes. The question, when it comes to graphics, is there a performance difference between Build 3D and Get 3D? Kind of, sort of. So the way build 3D works is it will call get 3D. It'll take that result and it'll put it into the model field. That model field is, in a way, a cache. Not in a way, it's what it is. It's a cache. And so in some situations where um, to implement. All right, there we go. Sorry, my headset died on me again. I need to stop poking things. In some situations, the get 3D approach can save you some time because the build 3D method is actually caching the result in the model field. Oh wait, did I get that backwards? No, I got that backwards. I'm sorry, I said the wrong thing. It's get 3D that calls build 3D. That's right. The caching actually happens inside of get 3D. So yeah, there is a bit of caching available there. However, in my testing, I've found that the caching does not hit all that often. That model gets cleared out fairly often. So is there a difference? I would say not a big one, but as always, run some tests and see if it affects you differently. Another question, what is the best way nowadays to avoid GC affecting your p-time test results? Pause, stop, then resume. Man, I don't know if I can, in good conscience, recommend taking any kind of manual control over the garbage collector. Just because it's so easy to get it wrong, to get bad results, or to even mess up how your garbage collector is running. What I've found in my test when I've done performance hunting is that level of control over the garbage collector typically isn't a problem. Garbage collector happens so quickly and it takes so little time that it's really hard for that to have a meaningful impact on the time measurements that you get. And so if you're running your test a bunch of times, or if you're running it on a large scale, anything like that, the time that you spend in the garbage collector is going to be so small that it just doesn't even matter in your results. If there is a situation where you really, really, really need to know that garbage collection is not going to get in the way, you can trigger a garbage collection manually by calling _GC, I think. That is the only thing I'm even remotely okay with bringing up, just because it's safe. There's no chance of it like breaking anything. But for those of you who don't know, calling _GC just says to the garbage collector, collect right now. And I think it only works in develop mode, now that I think about it. What is the best place to store the caches? Almost always as local as you can make it. If you have a value that's being retrieved from a specific file, then the cache should be in that file if possible. If you have a whole bunch of snappers that are sharing the same caching system introduced by a base class, then leave the cache in the file for that base class. Yeah, always try to keep it as local as possible to where the cache is being used. Question, could you please show the graphics slide with the get 3D code again? Yes, at least I think so. Let me try. Where is it? There we go. Okay. Are there any more questions or comments? Another one. You mentioned the probes method get optimized out in release mode build, similar to pre-processor directives in other languages. I believe so. I unfortunately don't have Emacs up and running, but if you look in the file that defines those probes, I'm pretty sure it's either probes or the profiler, but I'm pretty sure it's probes that actually have those pound if statements that won't actually have any code if you're compiling in release mode. Is there a list of those types of things? I'm not aware of that many actually. I'm aware of the if. Um, I don't know of any others. We generally don't use them. So there might be a list. I'm unaware of where that list might be. Okay. Um, I'm going to go ahead and end the webinar for now. As I said before, it's all been recorded and it will hopefully in the near future be posted to the Configure YouTube channel. Yeah, thank you everyone for attending. I hope it was helpful. Enjoy the rest of your day.